So it's a pleasure to have this week our seminar speaker, Seng, visiting from McGill University. He's going to tell us about anomaly-induced thermodynamics in higher-dimensional ADS CFT.
Thank you for inviting me here. It's a pleasure to be here. Today I'm going to talk about anomalies, finite temperature manifestation of that. And in particular, close to my heart is how do you think about this in ADS? At least some hint on how to think about it. So this is a work based on authors from a couple of years ago till last year. So I always start with this sentence. Black hole have entropy, and then there's an explanation part that's really quite interesting. Black hole have entropy. And black holes have entropy that's proportional to the area, and that's something that we've been fascinated by. It's very interesting. And then in string theories and various examples, we know how to predict that. What are the degrees of freedom responsible to the area? 1 over 4G, and then in this glorious detail. So these are all exciting and wonderful results. Now, the thing is, oftentimes this involves extremely black holes or supersymmetric, or I guess they are related issues. Now, when you want to think about more interesting things like dynamics of black holes, black hole evaporations, we usually have to go away from thinking about it in the SUSI or extremal case. The question is that, then in that case, how do we think about this black hole entropy? How do we count them, for example? So one of the setup where this thing could be addressed was in the 3D case, when you have 3D black hole. So these are called BTZ black hole. And the entropy is famously produced by this thing called the Cardis formula. So in ADS3 CFT2, if you have 2D CFT at high energy, the density of state grow in a way that if you go to canonical ensemble, this goes linearly, and the coefficient is fixed by the central charge. It counts the degrees of freedom in 2D CFT. So in 2D, there's a matching because of universality on both sides. Now, although 3D is interesting in many cases, so I'm in McGill, so the 3D gravity is a big thing. But it'd be nice to think about, is there any higher dimension generalization of Cardis formula? Because you can think about higher dimension black holes, they have entropy. Is there a way to match them that doesn't rely on supersymmetry or extremality? So this is what I meant by Cardis entropy matching. So the outline of this talk comprises of 2 parts. The first part involves reviewing what is called a chiral half of Cardis formula in higher dimension CFT. I'm going to explain, I guess, most of this work in the next few slides. So this is some work that people have done in the past few years, understanding anomalies, finite temperature anomalies, how it manifests itself in hydrodynamics. And the second part is things that we do, and is what I was concerned about. Now, if there's a field theory, so the first part is really field theoretical. The field theory, people have done this 10, 20 years ago. People only are starting to understand it recently. There's some result coming from, in fact, even quantum field theory, you can say the same statement. But let me restrict myself to the CFT for the rest of the talk. There are this set of results, which I would call replacement rule for obvious reason later on. This set of replacement rule, how do I think about it? Firstly, is it true from ADS CFT? If you do an ADS calculation, do you get that result? And secondly, is there any geometric way to think about this result? So that would be sort of the theme that we're starting to uncover. So to put it into perspective on all these various pieces that I want to talk about, let's consider the 2D case that we understood reasonably well. Consider 2D CFT on circle times. So circle of radius r. Now, when I say put it at finite temperature, I meant you either do canonical quantization and count the states using Boltzmann factor, or you just do a path integral over S1 cross S1, where one of the S1 has beta, which is 1 over t. The other S1 will have radius r. So torus partition function, give you a CFT, compute that, you spit out a result. In 2D, this result has a very, very interesting form when you have high temperature. And this is true for any CFT2, let's say unitary CFT2, so that I don't deal with some subtraction of the stuff. So this is the result at high temperature in 2D. Now, probably you're more familiar with this piece that is proportional to C left plus C right, and is linear in the temperature. So this is what is called the Wald anomaly, or the trace anomaly, or the scale anomaly, depending which one you prefer. So whenever you put a CFT on the curved background, or in this case at finite temperature, it pops out this anomaly that has to do with the scale transformation are not exactly symmetry at the quantum level, and this is the manifestation. So this we know. And the other part that was usually less talked about is the part that's related to the gravitational anomaly. And this part is proportional to omega. If you ignore the omega square term, this term is proportional to omega, meaning that it breaks parity. You can do phi to minus phi, where phi is the coordinate here, and omega will switch sign, and this term is parity off. Now this term is proportional to the number of right mover minus the number of left mover. So you have n number of left mover, this is proportional to that up to some pi's and stuff, and this is the number of left mover. And it's also linear in T, and this is what I would call the chiral half, or the anomalous half of the Cardy's formula. And the aim for the rest of the talk is to tell you in high dimension how does the formula look like. There's a definite answer. And then to try to match it. So this result has been matched to 3D BTZ when you incorporate the gravitational anomaly in the bulk through what is called the gravitational consignment term. So if you're familiar with 3D gravity, those theory are called topological massive theory of gravity. So this we understood and we know how to match them.
What was omega?
Omega is the, sorry, it's the angular rotation. So, or the boost, I guess, in 2D is. So I put it at fine temperature beta, and then when I go around beta, the field's going to twist, will be omega. Thank you.
So you put the CFT in curved background to get this result?
Well, you can, usually you get this C left plus C right, you put it on curved background. But in this case, right, put it at final temperature has similar effect as thinking about it as you're turning on background field, right?
2D background.
2D.
Not 10D or anything.
No, sorry. By background, I mean this is QFT still, right?
QFT background. Okay.
Any question? So again, let me just put a norm in every formula to say that's the anomalous part, and just to keep it there. Now to generalize this to high dimension, consider CFT on this kind of geometry, on a sphere times times. The reason put it on a sphere is a lot about thermodynamic quantities are density. They are finite only with the density, thermodynamic density are finite when you take the radius of the sphere to infinity. So we have to do it more carefully. So I kept the radius of the sphere there. Good. So this in high dimension is called replacement rule. I'm going to show them and motivate how they look like in the next few slides. By some of these people, and we have a few more that I might not have space to put in. To talk about how the result looks like, I need to first remind ourselves the zero temperature anomalies. Now, maybe most of you guys already know this, but just to, I'm going to flash one slide because it's not doing it justice. What is T equal to zero anomalies? And the way that we're going to think about it is going to be useful for the result I'm going to describe. So there are, of course, other ways to think about this. And then more unknown is how anomalies enter into hydrodynamics. In fact, I'm not going to describe not the final temperature piece, but in hydrodynamics when you do it in some derivative expansion. I'm going to show you, I'm going to discuss both of these in the next slide. Now anomalies are, there are many names associated with this, but I'm going to talk about something called anomaly inflow, which for me is the most economic way to do calculation of capture anomalies. So anomaly, just to be clear, I'm talking about global continuous anomaly. So these things are there. You have chiral fermion with 4D, 6D, you have gauge, and
well, a moment ago you told us they were gravitational and wild. That doesn't sound global. So why do you now? I'm confused. The anomalies you told us a moment ago were local anomalies, were they not? These guys.
Skewed conformal transformations are global symmetry.
Global. What about gravitational?
It's a QFT, right? So these are all background field. So I'm not gauging the gravity.
Yeah, it's not covered into the gravity.
I'm not doing string theory, so this quantum field theory in 2 dimensions.
So as far as 2D it goes, we are saying
in high dimension, I also think about couple. If I turn on a gravity background, but not dynamical. So these are all global symmetry.
Oh, okay. Thank you.
Indeed, in string theory, you do want to use them. That's why you need the central charge to be zero.
Yes. But string theory, you sum over them, so there's trace vanishes.
Yeah.
So let's talk about string theory. Good. So to me, the way to think about anomalies, one way to think about it is to think about conservation loss. If you have the symmetry, something is conserved. If there's not, at the quantum level, that this thing is at least, let's say 1 point function or incorporated, it doesn't vanish. So if it doesn't vanish, it means the symmetry is not there at the quantum level. Global symmetries are broken. Now you can do all this triangle, hexagon combination, and the way to summarize the result, at least because this goes back to like 10, 20 years ago, is to think about consignment terms. So this is anomaly inflow. So this picture has nothing to do with ADS-CFT. Let me stress that. So if you have a QFT2F, it's more convenient to put it on the boundary of a three-dimensional manifold. In auxiliary, you can extend by line, by sphere, it doesn't matter. As long as you don't affect the dynamics here, you can extend it in any trivial way you want. But in 3 dimension, or 2n plus 1, in odd dimension, there's no anomaly because there's no chiral fermions. So if you think about the partition function on this 2n plus 1, right, you should not get any anomalous conservation law. All conservation laws should be satisfied, and partition functions will transform in the right way without anomaly. And the way to think about it is that if you do it in this way, in 2n plus 1, you should include something called a Chern-Simon term, so that the non-conservation of the QFT 2n are captured by these 2n plus 1 Chern-Simon terms. And morally, you can think about the non-conservation of the 2n dimensional QFT is captured by some charges inflow or outflow, hence the name inflow. And this inflow has to do with the currents associated with this Chern-Simon term. Now, the Chern-Simon term is an odd form. That's why I need to do it in 2n plus 1. And if you think about this as a form without worrying about dimension, the D of that is a 2n plus 2 dimensional form. And why do I want to do this? Because if you work with Chern-Simon term, they are almost covariant. They're covariant up to the boundary term. And sometimes the boundary terms do matter, and you have to be very careful. Whereas if you phrase it in terms of anomaly polynomial, so this P anom is also called anomaly polynomial. This is always a function of the gauge field, thinking about it in terms of form. And Riemann tensor, if you rewrite it in terms of form, is the Riemann 2 form. It's a polynomial in F and R.
Excuse me, if I quantize Chern-Simon theory, I could engineer boundary conditions on the gauge transformation parameters and the gauge fields in such a way that it's exactly gauge invariant. In other words, the total derivative terms I can engineer to.
Right. So you think about WCW model in the boundary.
In any Chern-Simon, so if I do that,
sure.
Would you say that there's no anomaly inflow? Is that, I mean?
Sure, sure. So there's a 3D dynamic gauge field. Then you have to do a path integral. But here, the gauge field are all background. I don't do a path integral over them.
Even in the Chern-Simon theory?
No, my Chern-Simon theory is that, so consider the path integral of 2n or 2n plus 1 theory, turn on some background, you path integral over all the fermions, but it's a functional of the gauge field. The gauge field is a background field, like the metric and all this. But as you say, if you give me a dynamic Chern-Simon term and you path integrate, you can turn on Wilson line orders and those are gauge invariant object, yes. But here it's important that these are background field. The metric, the gauge field are all background. Good. And just in case you ever want to do computation with this, so if the anomaly contents, right, I guess one of the key results of Kellen, Harvey, and Bardeen and other friends is that all the anomalies informations are captured by left-right movers, the net of that, and that can be succinctly described by anomaly polynomial. I'm going to give an example about 2D and some example of the anomaly polynomial. It's sufficient to say that there's some polynomial in F and R, and the coefficient, right, tell you how many left minus right mover you have, and that is enough content for anomaly. Once you give me that, right, I can tell you, let's say, how non-conservation law behave, and all the information that you want in terms of correlators. So again, it's important that anomaly polynomial is capture the content of your anomaly. Any questions? This is really fast because usually I go to a review and it's like 100 or 200 pages of lectures. This is now I need to talk to you about hydrodynamics, which another chapter is in Landau, and then anyway, so this is one page summary of hydrodynamics.
That's optimistic.
Yes. The hydrodynamics, we probably have heard of it. We have water, we have stir water, and then we know hydrodynamics. Hydrodynamics is a long wavelength description of physics. One of the postulates is that there are macroscopic variables called velocity because fluid flow, there's fluid flow, and there's temperature. If you have a charge, the chemical potential, and then maybe a few more if you want some other conserved things. And if you turn on background field, you can turn on charge, or you can turn on some bias or electric field. You can put it on curved space with a sphere, shake it. You can do tons of things. So you can turn on some background field. Hydrodynamic, I guess, assumption is that there exists a hydrodynamic derivative expansion, meaning that the one-point function. Let me just talk about CFT. The one-point function in the CFT, I guess in that case these are related, and the currents have a very nice form. First, these are the perfect fluid. So you work with perfect fluid. This is a perfect fluid form. And there's energy density. There's a pressure. This is all zero derivative, all the hydrogens. Very interestingly, all the dot dots, one first order, second order, there's all this viscosity that you might have heard about, and all these various things that I'm not going to write about that because those are parity events. But today I'm going to talk about the anomaly-induced part. Now they are distinguished and meaningful because they're parity odd. And if you open lambda, right, in fact they did not include any of these. So this only were rediscovered in the past 5 years that why not include parity odd term? And the reason to include it is of course because of anomalies, because these are induced by anomalies. So for today,
would it be still physical situation?
Sorry?
Would it be still physical situation if you turn on this? Are there hydrodynamical real systems in which this parity violation?
I'm going to tell you in words what I know about some condensed matter system. There's something called wild semi-matter. Somehow, in some effective theory of condensed matter, there's some left-moving chiral degrees of freedom. And those cases, right, if you put it in hydrostates, this is supposed to come out. So, yeah.
Well, they are physical, although we call them anomalous.
Yeah.
Basically because there's no local symmetry. Well, that's the right one.
Yeah. Or you can think about this that sometimes you have a 3D system and then there's some way that you can gap it so that there's some left mover on one side and right mover on the other side, so that in total it cancels out. But if you just probe one of them, you might see this.
Because this calculation will be different from triangles for this case.
So this is finite term.
And it calculates its viscosity and so on.
Yeah.
In this way. It will be different from calculation of conventional anomaly through triangle diagrams.
So triangle diagrams are for zero temperature, right? The analog of that for finite temperature should be the same as this. Yeah. You have to sum over multiply over and all this. Good question. So in fact, that's how they. So to fix this term, you take a grab partial alpha of this and demand that this to reproduce what you expect from triangle or the finite temperature version of triangle. Good question. So one caveat, I'm going to tell you, so these parity odd terms also have derivative expansion, right? There might be n-1 order, and then maybe another one higher or two higher. I'm just going to describe the leading one that we are going to match. People know how to calculate this, and in higher derivative, if you have higher than the leading one, you have to find some funny thing to describe it, which I'm not going to do. So I'm going to tell you the leading one, which seems very nice, and you see why. And you see, if you want to have parity odd, the first thing you do, you put in an epsilon tensor. Just like in term, right? If you have any parity odd thing, you put in an epsilon. And now, what tensor has to be proportional to? Well, you put u there, you cannot put 2u because epsilon is 0, then you put grad u turns out you can make any number you want. So it turns out the first leading thing in the 2n dimensional theory is that n-1 derivative term. And this in high enough dimension is really high, like, well, I guess, depending how many dimensions you go, it can be as high as you want. So these terms are there, and they're proportional. The leading one is proportional to this v. I guess I can say this is called parity of vorticity. Yeah.
Why is that related to an anomaly? Shouldn't there just be a vorticity term in your hydrodynamic equations?
Sorry, what kind of terms do you have?
That's the one you wrote, just this velocity
So
gradient.
this is the parity odd term, and this is really the anomaly. You're thinking that there's a contribution coming from the.
Why isn't it just in the first ellipsis, for example?
Because all these things, all the black things are supposed to parity even. This thing is parity odd.
At the moment, we can just say it's parity odd, but to call it anomaly takes a little more
Yes.
explanation, right? But for now, we can just say that's a unique parity odd term.
Yes. You're worried that this thing comes on. I think maybe vorticity, you're thinking about, there's another word called vorticity that uses slightly differently, which is not this parity odd term.
It's more like when you say anomaly, I think quantum, and I don't know why this is.
This is a one-point function of J and T, is a QFT.
Oh, could it be that it's not divergence free, by the way? If I take J alpha and take divergence, will this term
This
be
is
wrong?
not going to be
Will not
This
be
is
zero,
going to
but
reproduce
there's
everything.
Okay.
Oh, you're thinking about if it's conserved, then this should be okay.
Okay.
Sure.
Similarly for the
Yeah, that's
other.
good. Thanks.
Okay, this is a one-point function in the QFT, and this is supposed to be include all the. It's not supposed to be a term. This is the full answer of the one-point function. Any more questions? Good. So now I'm going to tell you the result of this thing. I can say a few words about how to derive this. extremely tedious. So I motivate that this is a unique parity odd term, and if you think about it, this is the first leading inderivative odd term. So let me just say that in the currents, there's a term that's proportional to V alpha. Let's concentrate on the normal term. And in T alpha beta, because it's symmetric, it's proportional to V, this is the only thing we can get. Now the non-trivial things are all hidden in these prefactors. Now again, we are talking about one-point function. So one-point function, what can it depend on? Well, because of Lorentz symmetry. I guess in this case, the final temperature case, we can, besides from these indices, the only thing that can appear is temperature and mu dependent functions. So I'm claiming that from this result, these people derive that it can be captured by one function called curly f, and we take various derivatives, and this is supposed to capture all the prefactors here. So just to motivate why this doesn't look too foreign. Remember that in Gibbs free energy, maybe some years ago, if I have Gibbs free energy, I can take various derivatives. I can take how it responds to chemical potential, give me the charges, how it responds to temperature, and some subtract it the right way, it gives you the energy. And if you keep everything fixed and just look at the response with respect to temperature, it gives you the entropy. Now, so these people, what they told us is that anomaly contributions can be captured by one Gibbs free energy. And once you know that Gibbs free energy, you can take various derivatives, and they give you all the answer in one-point function you want, and as well as in the entropy. And this is proportional to, so rotation, you have to turn on all rotation in the two-dimensional QFT on.
Who showed this?
So this is work by Logan Diagram, Kristen Jensen,
Not too long ago.
yeah, maybe 2-3 years ago. I can say in one sentence what they did, which is a series of 3 papers, each of which more than 50 pages. You put it on, so in anomaly, right, or in hydrodynamics, you write out all possible terms you have by symmetry with some coefficient, and there are coefficients that depend on T and mu in some way. Now, you consider a partition function of a QFT2M, that's anomaly. You know that there are all the variation, if you vary, you give you currents, if you T, they give you all these terms. But you also know that it's supposed to be captured by a Chen-Simon term in 2n+1 using this anomaly inflow. And insisting that the Chen-Simon term, when you do all these variations, reproduce things that cancel this in the 2n+1 theory, fixes all the various coefficients. Now, the trick is that you have to put it on different type of curve background, not gauging, not dynamical background, but just background of metric. And if you put it on enough distinct and useful background, you'll be able to fix all these coefficients. And the end result is this, summarized in this result, that there's a Gibbs free energy function of which you derive, at least the leading one, derive all the response function, how it depends on T and mu of anomaly hydrodynamics. So that, I'm going to give some example. Of course, the question is that what is this F, and how do you obtain that? Let's step back to 2D Cadiz formula. I always use this example because Aristotle people are more familiar with this, but I can explain it slower just to be sure. So again, this is the formula that I told you before, but I make it into small omega because I want to think about the leading hydro when they have small rotation. So this factor is because of that. And then there's a linear in T, as I told you before, and there's a C right minus C left. Now, in 2D theory, when you have gravitation anomaly, I told you that all the anomaly contents are given by the anomaly polynomial. So in 2D, right, you have to go to 3D to get a Chen-Simon term, and you go to 4D to get an anomaly polynomial. Now, if you think about just pure, so these are pure gravitational anomaly. I give you a Riemann 2 form, I need to give a 4 form. So you get trace R squared. So this is what it is. And the coefficients are determined by, okay, depending on the convention, there are always 2 pi and 24, but more or less it's C left minus C right. So this captures C left minus C right of your 2D QFT or CFT. Once you have this, right, so you observe that this is linear in temperature. If you replace trace R squared to T squared, you take one derivative, you get linear in T. Now this seems to be just some weird manipulation, but in high dimension, this turns out to be the right manipulation to describe the answer. Let me show you the next slide. Any question about the 2D reinterpretation of
Great. I'm going to explain why you should place trace R squared with T squared. I wasn't sure if that's what you're saying.
That's why, I'm using this slide to motivate it.
Okay,
to
that's
see
fine.
the sense.
Yeah, well, how do you, indeed, this equality between the two, what goes into it in the nutshell? That trace R squared is equal to this. We can calculate this anomaly like in any given dimension, right?
Yeah.
If there's, but again, only if there's gravitational fields coupled to,
You can always
that,
come down to the background
coupled to chiral fermions. Say.
Right. In 6D you can get.
So in 2D, if I were to do it, I just count the number of left-handed and right-handed fermions,
Exactly.
and then that will be the coefficient of trace R squared. How do I get the exact relation to this? It's not clear. CR minus C left minus all that stuff.
Oh, you're worried about C
Mhm.
right minus C right equal to
Is
C.
that the difference between chiral and anti-chiral fermions? or
Yeah, so
what?
C left minus C right. In some convention, it's just that. So forget about
Yeah.
that. So CG and this right, that is, that's true.
And the T enters because you're doing a finite temperature calculation or what? It's 2 pi T. That was your question.
Yeah, I mean,
Two
I
pi.
Yeah.
wasn't sure if I was supposed to be thinking of R as really a curvature on some space.
Right, so this is more a formal statement to describe the answer. Because my background is always S1 cross S2n minus 1. I compute partition function like that. I compute all the thermodynamical density. I never change any background. I never, right. But then this is saying that this is a trick to say that if you give me the anomaly content, so this is a trick to extract the coefficient of the anomaly point if you want. And then the t square, if you like, more or less fixed by dimension, and to get the correct coefficient, you have to get all the pi.
What is your low energy scale? You're talking about that you're looking at high temperature, and there should be high with respect to something, and you're starting to need this.
So,
there should be all powers of this ratio.
Yes. So this is the leading hydrodynamic result.
So it's not so high, it is next.
Next to leading, you mean?
This is the
Next
unit.
to the lowest power.
Yeah.
Because if you have some scale,
Mhm.
there should be all powers of
Yes.
T over this
So
scale.
the parity even terms have various power. The parity odd term, this is the leading one. This is the first
So
one.
it is some special.
Yeah.
Okay.
And the temperature is greater than the size of the sphere. So that's why
But maybe the derivatives, you're expanding in derivatives. Right?
yes. Or you can think about
the
yes.
derivatives of the small parameter.
Right. So rotation over temperature. So this is a summary of what is claimed. Anomalous contributions are proportional to V, the leading one, and it's given by this Gibbs free energy. And the Gibbs free energy are, we give me the anomaly polynomial in high dimension, N2n. So sometimes you can also have gauge field with anomaly, not gauge anomaly, but just global gauge field. And I guess sometimes you can have mixed term and all those things. And the rule is that whenever you see F, you will replace by the chemical potential. Whenever you see trace R to 2K, you replace it by 2 pi T to 2K. Honestly, I do not really know how to physically motivate this. It came out from their computation by saying that they will fix all these coefficients, and it turns out that all these coefficients are related to the coefficient that appear in the anomaly polynomial. And then, so that's how you fix it. And there must be a better way to see this, although all these authors, they also feel a bit contrived that it's a result that's so clean and so simple. So just to illustrate how to, let me just go to the example first. So if I give you another example, maybe you walk me with that question. So in 2D, there are two types of, if I just consider U1 abelian gauge field as background, there are two types of anomaly. There's gravitational one, which described, it's a CG, which is left minus right, and there's also F squared. So this is just a gauge field. And the anomaly polynomial, I replace F by mu, replace R squared with T squared. And in 4D, they are slightly more structured because you can mix two of them, basically multiply F on the whole thing, and you can get something that looks like mu T squared and mu cube. 6D, there are in fact two types of pure gravitational anomaly, trace R to 4, trace R squared, and let's talk about one of them. And the difference between the free energy for those things are a factor of 2, so it's not that different. So the free energy, the Gibbs free energy for the anomalous part is T to the 4. So this gives you all the, so these are free energy density. So if you like bi-dimensional analysis and you believe that you're talking about anomaly, there's nothing that should come in, then it should give you like T to the 4 bit power. The coefficient is harder to motivate, but that's temperature dependence.
But in particular, you said in 60, F can't distinguish between the two gravitational anomalies.
The temperature dependence is
It's only
both
sensitive
to the form.
Yeah, it's only sensitive to one linear combination of coefficients.
So in other words, if I take a combination of r to the 4 and r squared square, do you know how to determine f?
We know how to determine F, but I think what he says is that you need to depend linear
You can
combination.
go backwards. Oh, I see.
So, I think this,
I see.
another thing is the only depends on the contrarian class form.
Yeah.
Second or fourth.
The fact that you can go the other way, would you consider that an open problem? Or is it something not very
I'm just saying that with the leading part doesn't distinguish. Actually, I'm not sure whether the sub-leading term in parity octave will distinguish. Yeah. So, but the leading one somehow doesn't know. You only need to know which power of R you are and sub-leading combination.
And yeah, I can have a mixture of also
F,
F's, right?
Yeah, F squared trace R
f to
squared.
the 4, f squared square.
Yes, yes, yes. So this, yeah. I didn't write it because then I just keep writing.
By the way, is it important to have a billion f? Or
No, no, no.
You could have non-abelian.
Yes.
The story works.
Yeah, so you be a trace on all these things.
Mhm,
And,
okay.
the replacement rule, I guess, yeah. So you just have to go to the katan and replace the katan to compute temperature.
So if f is non-abelian, then mu will be some matrix.
Mu will be the charge, the katan of the group.
Ah,
What you chemical potential for that.
okay.
Good question. So just to repeat that, if you have a favorite QFT or CFT, you know that it's anomalous. That's the left minus right. You give me the anomaly polynomial and you ask me what's the one-point function in the hydrodynamic states and what's the parity of one. So this is the answer. And for example, let's say that in 4D, there's a term in the current itself that's proportional to temperature squared because I take 1 mu derivative. That's proportional to V. And then in energy, you can work out the same thing. And for the anomalous contribution to the entropy, you can just take T derivative. You see that if you do not have gravitational anomaly, pure gauge anomaly, meaning the global gauge field, then they do not enter the anomalous part of the entropy. So which is somewhat sensible because we always think about, well, entropy is like, you think about quantitative effect, computation is like how background gravity responds, so you better be that you have to think about gravitational mixing of the gravitation.
And in 60, life can get very interesting, right? You
Yes.
can have Safdie forms,
Yes.
and they will also contribute. So,
Yes.
all this is about the well-known anomaly
Yes,
analysis,
yes.
which you take, and you have a dictionary to
Yes.
translate it into
Yes.
this. That's what you're saying.
Yes. Yes. So the form, I guess in 2D you can have cell-dual boson and current boson.
Hmm.
Yes. So all these things, you give me the anomaly polynomial once you work it out, what's the two factors, this is the answer. It's universal in that way, it's non-universal in the way that it depends on the anomaly polynomial, which is what you should depend on then.
Mhm.
It cannot be.
And supersymmetry doesn't play any role in this.
No at all.
And if I were to put in supersymmetry in this,
Asymmetry anomaly could go in here as well. The SO file.
so there will still be anomalies in SUSY.
Yeah,
Supersymmetry.
you can. So good. So the first half of my talk was over, and that was to recap this result of replacement rule. If you give me an anomaly polynomial, I can give you one-point function of stress tensor and currents, the anomalous part, and also the entropy contribution. Now back to what I initially tried to motivate. Now, we want to test ADS-CFT. Now even in the earliest paper of ADS-CFT, anomalies was present in before MU, all these asymmetry anomalies, you can look at all these triangle anomalies in zero temperature. Now I want to test it in the finite temperature case. And I want to test it in the way that hopefully I can think about in the bulk, what kind of bulk? Is there an interesting bulk object that capture this anomaly contribution? Unfortunately, I won't have anything to say about, anything very concrete to say about this. Although we have tested it and of course, they do match, otherwise I won't be talking about that. But I will tell you how we match and then maybe say a few words about some structure develops. Now, so if you are a holography or holographers, your recipe is always this. Find a particular theory that you care about. Sometimes it's toy model, sometimes it's realistic embedding in string theory. First, write down your favorite ADS bulk theories. Now, in this case, the bulk has reproduced some non-conservation occurrence, and this turns out to need some gravitation or gauge gravitation for these. The next thing to do is that now, so what kind of state you want to study? If you're studying about final temperature state, you have to look at the relevant ADS black holes. And if now we're talking about hydrodynamic black hole, hydrodynamic state, so it's an extension of this thing called free gravity that I just mentioned a few words later on. So we need, and also we need to turn on enough rotation because there's some parity thing that we need to turn on, or rotation of charges. So we need ADS Kerr-Newman with Chen-Simon term turn on. So as far as I know, this is very hard to find a general solution to this. I think people know how to do a Chen-Simon term for a gauge, like A wedge F squared 5A or something, but if you have gravitational terms and you want it for arbitrary charges or N notation, is almost impossible. People haven't written this down. So this is another issue. The third thing is that if you have worked with TMG in 3D, sometimes your Chen-Simon, you see, when you derive charges, right, you go to the non-linear procedure, you vary your action and you pick out the boundary term. The Chen-Simon terms is precisely those that give you a boundary term that's not covariant. So you have to think about that carefully. And then you can do a holographic normalization of charges. And even for entropy, I'm going to comment on it at the end. There's some subtle things about Chen-Simon terms that you have to worry about. Once you figure this out, you compute all these one-point function and entropy, and then you see whether you match or not. So this is the idea.
Why do you need all the charges?
So it's parity odd in the sense that in 2n dimension, you turn on all n rotation of the sphere. That this du that you saw, actually they're all omega, if you like, for all these.
Because you're using epsilons, so you got
Exactly. Yeah. That grad u, right, has many independent components, and if you want all of them different, then you get otherwise that's okay.
Yeah, just in your replacement rule, it looked like you get away with just one flavor and one rotation in the replacement rule. No, that's okay. Yeah. So here you could have had different flavors, for example, right? For different Fs, and you would have had different mu's, but that's about it, right? And then, but you don't.
Like this,
But here it seems like you only need one.
Right. So that's the replacement rule, but here I guess I was thinking about, right, so in terms of this, you don't worry too much. But V secretly, right, captures, V would be 0.
You have a product over omega I.
Yeah. So here I sort of wrote down star V out. Like the V is just this one.
And those are all the n rotations you were talking about.
Good. So eventually we want to check this in some more realistic setup. But for now, right, remember that if you remember in the case where people matched wild anomalies and the A theorem or the C theorem, somehow a lot of the physics were captured by just the gravitational sectors of the theory, that you can have gravity plus appropriate hydrogen term, if you want to think about it, plus matter, and that in some truncation supergravity is your setup of ADS-CFT. So some physics should be captured by the gravitational part. So if you study pure gravitational anomaly, it should be that Einstein plus Chen-Simon terms plus negative cosmology. Maybe in the realistic thing, plus some matter, gauge field, and all those things. It should be that some of the physics are already captured here. Plus, I guess if you add matter, you complicated things, and we wanted to try our hand on the first thing that works. So our setup is very simple. This part you're familiar, just Einstein-Maxwell equation. Maxwell is here. In this case, the Chen-Simon term also induces something what we call Horseradish Tensor and the Hall currents. By Hall, because a lot of these derivations, because it involves Chen-Simon terms, when people do quantum Hall effects, it's interesting to think about it in terms of a bulk, 2 plus 1 bulk that has a Chen-Simon term. So, but anyway, if you don't care about
Chen-Simon term doesn't depend on the gravity, on the matrix. How can you generate?
You're thinking about gauge Chen-Simon term, A wedge, dA, some kind of thing. But this is
yeah,
gamma wedge
this
d gamma.
Lorentzian Chen-Simon, sorry, yeah.
So this is gamma wedge d gamma squared. That's
Of course, sorry, okay.
Yeah, okay. Good question. So if you don't care about this subscript H and whether it makes you less comfortable. Think about this, you just capture
It makes me nervous. I don't know what this means.
Yeah, because Hall people.
H for all.
Yeah,
Okay.
yeah.
Okay.
It's the same computation when you do quantum Hall effects. You write things conscious. But the currents looks like. So again, the currents. If you want to solve this equation, I try not to write ICS for a reason that because if you do it, you have all this gamma floating around. At some point, you see this is supposed to be covariant. The equation motion is supposed to be covariant. If I write this in terms of ICS, then at some point I run into non-covariance unless, well, you wouldn't be manifestly covariant. So the way to write manifestly covariant is to think about the anomaly polynomial again. It's again a polynomial in F where I take star d of a, this is covariant. So equation motion are manifestly covariant if I write it in this form. And in TMG, right, in 3D, this contribution is called a Gaussian tensor, if you work with that. And this is a generalization of the Gaussian tensor. It's sort of covariant derivative, it's a divergence of derivatives of P respect to R. So this is a compact way, it's manifestly covariant. If you want to work on this, I would recommend doing it this way. But once you have this, you decide, okay, what kind of metric you want. So this is half a page summary of what fluid gravity is, which is, of course, most of that paper is like 100 pages. Fluid gravity is a dictionary in ADS-CFT. Let's say if you work in hydrodynamic states in the CFT, how do you compute anything in gravity and match that? The way to do it, one way to do it is to think about it in an intensification time frame. And right now, you remember that in hydrodynamics, I told you that it's an effective description that says that you have U, which is the velocity of the fluid, and also temperature and some of the microscopic variable. And the way that fluid gravity works is that all these are supposed to be the fluid velocity in the field theory side. They're supposed to appear in a particular way. And then if you have turned on some background metric, this is a boundary background metric. It has to appear in this way. And if you work with black holes in ADS, you realize that the leading answer looks like a free ideal gas. And this is what, if you ignore all the high order terms, this at the end of the day you get some ideal fluid answer. And then there's some second order thing, and later on I'm going to add a few more things. So there are some free functions. Here is f and here is phi. It depends on radius and some charges like mass and q. So if you ignore everything, it looks like just a planar black plane solution. And so remember that aside from the velocity, there's also the chemical potential and the temperature. And this is important, so this phi, right, looks like 1 over r to some power, and there's a q. At the horizon, it's supposed to be identified with the chemical potential. And remember, so this is a bit like dt squared term, because u of t is like, u of t is 1, and this is dt squared. So remember that in front of dt squared to get a surface gravity, you take one derivative. So it's in fact the derivatives of f at the horizon that give you the temperature. So this is just retranslation of a lot of things we know. But here, you can do a lot, you can do more. And that includes higher order correction and solve Einstein equation in the hydrodynamic expansion. And people have looked at interesting things like viscosity and all this things set up. Now the ingredients that we're going to get is that what I'm going to put in is that now we're going to look at anomalous charge rotating fluid. What's the gravity dual of these? Now I say that we do not know any exact solutions that does this. So and plus I described for you the hydrodynamic part of it. So it's easier and more convenient to think about the gravity dual of the anomalous charge fluid. Now again, because you have UV and that's the symmetric part that you can write down. There's some function here, and here, like the charge, the current is proportional to V, and there's some function here. The whole goal of is to plug this into the equation motion that I told you, and extract G and A. Once you know the metric, and appropriately not mixing orders, you have to be careful about order. But once you're careful about that, the rest is just involve solving A and G and how they this is a back reaction, if you like, how they back react into the stress tensor and the one-point function in holographic renormalization. Now so that now is probably straightforward, and there's only one observation that we observed that was useful and maybe curious. So remember there's a replacement rule in the boundary which says that if you take a anomaly polynomial, replace some of the mu, replace some of the f with mu, t, r with t, and you're supposed to get the contribution in one-point function. Here, right, the gravity way that this works, again, gravity equations are very mysterious and they contain a lot of physics about the field theory that It's just not obvious. These TH and JH, you can repackage them into some derivatives of a master function called G. More speaking, is 1R derivatives and 2R square derivative, because if you think about dimension, and also because it contains two derivatives, after you take a derivative with respect to phi, this is the structure that appears. And this is what we call the bar replacement rule. And this master G, right, again, has a structure that looks like a field theory. Now remember phi, right, at the horizon is equal to mu, and phi t at the horizon is equal to the temperature. And the phi t comes from the derivatives of the equator. And this at the horizon precisely is what curly F is. And the way this works, after you crank, you have collaborators that crank the dots, and then you put this replacement rule into the metric correction A and G, and then you do the standard Brown-York, or if you like, pick up R component of the F, the boundary stress tensor currents. If you do that, you realize that the anomalous contribution of these are proportional to U, V, and V, and the coefficients are exactly what you expect from the field theory answer. If you like, this is with derivation of the field theory answer in the graph. And at the horizon, this thing is precisely giving this.
So here the temperature really is coming as components of the non-tensor involved.
Temperature is, sorry.
Well, sorry, no wait.
So let me just flash back. So this is just, so G is defined this way. So anomaly polynomial, right, comes from the fact that you have a Chern-Simon term, sorry, what's the action? There's a Chern-Simon term in the action. For example, in 3D, it's gamma d gamma plus gamma cube, and the anomaly polynomial is trace R squared. So if you like, it's the former thing. Maybe you're trying to put it at, it's not the Riemann tensor of this thing. Although, maybe there's a way to think about it, but I'm not sure. So at this point, it's just, this is a formal observation that for any ICS, some polynomial, you can do this, the equation motion looks like this.
Yeah, I guess I was looking for something else.
Right, right. But maybe there's something to be, I don't know.
I mean, at least here the temperature is coming, you know,
This
phi t was a derivative of some component of the metric, taken to the boundary.
Mhm.
So like, Riemann tensor is also derivatives of the metric.
That's right, that's right. That's right. I empathize with the sentiment. Yeah, it'd be interesting. Let me think about it.
But if all you need is the anomaly polynomial, why do I have to worry about this detailed form of the metric you presented? If you go back.
Well, the boundary is going to, the boundary is supposed to be in the hydrostates, right? So in the bulk, you have to prepare what's the dual of the hydrostates, right? So if I compute it in zero temperature, then in the bulk, I just have ADS, pure ADS. Now I need to heat it up, I need to have hydro. So this is the way to prepare, if you like, this is the way to prepare an anomalous charge feeling fluid in the bulk. If you have a rotating black hole with rotation and the soft Einstein-Maxwell Chern-Simon theory, that would be the dual of a finite temperature anomaly.
But how unique is this solution? You read it on the board. I mean, on this slide, I could have imagined some other black hole solutions with different charges. Or
Many black holes in the hydro expansion will look like this.
it's universal in a way.
This part only depends on the anomaly polynomial, but for example, the second order and third order, different black hole will have different viscosity. Well, in Einstein theory, you only have one viscosity, but there are higher terms that.
So those could be different.
Yeah, and you can have hydro terms. So here I'm not saying. At the end, I'm going to talk about if you're not in the stationary solution, you're not in thermal equilibrium, hydro still works. And in fact, these results are independent of stationarity or not. So since there's two explanations, but also it was nice that there's some sort of bulk geometric. I'm not sure if it's geometric bulk replacement that then all these things why it works is because of there's a bulk replacement rule. We never understood how this bulk replacement rule comes about. I'm not sure whether it's, although this is at the end of the day you're solving an Einstein Maxwell Chern-Simon equation, and then there's this thing like. It would be nice that you say it would be related to Riemann or maybe some geometric structure of this charge rotating anomalous black hole. So that is still an open, ongoing thing. Okay, last slide before. So there's something that I haven't talked about, which is entropy, because I started with black hole entropy, and so I should finish with black hole entropy. if you work with higher derivative theory before, you know that there's a Watt entropy formula. In GR, that's the area function because it's GR. In higher derivative theory, you have to take the derivatives of Lagrange with respect to the Riemann. And this is how in GR you give just integral of the area. But the higher Watt derivation crucially says that they do the Noether procedure with some boundary terms and assume everything is covariant. Now, when you have just 7 terms, right, you have to worry about this issue about boundary terms being non-covariant. And in Tachikawa's, usually Tachikawa sort of figure this out for 3D and then sort of say how to do this in higher dimension. It almost looks like what you would do in one formula. You take a derivative with respect to the Lagrangian, but here you take a derivative with respect to the anomaly polynomial and you take 2k derivatives for each trace R2k that appear. For example, in 2D CFT ADS3, this is a trace R squared, so you get integral of gamma n. So gamma n, if you have a codimension 2 surface, you can think about normal connections and tangential connections. And there's always, because of this 2n, you can always have freedom to rotate them. There's an SO2 normal bundle, and this is the gamma n and Rn. You can take gamma n and take a d of that, give me Rn. So this is normal connection and normal curvature. Again, in the case of 3D, right? So you'll be given by peak a pi gamma n. And gamma n is interesting because gamma n is almost non-covariant as an diameter. If you take a variation of this and if you integrate over closed surface, it doesn't give non-covariant thing. By itself, it's non-covariant. And this formula is covariant if you integrate over closed surface.
What dimension are we in?
CFT is 2n and P anomaly is 2n plus 2. So integral of gamma n is 1 dimension in 3D, so we get convergence. So having this formula, plug in your fluid gravity metric, of course, it does match. It's not, it took us a few appendices to really do this properly. Hence, opaque, long, tedious. So in this case, we didn't find any replacement rule structure in the bulk to imply this. It'd be important to think about this because I think there might be some bulk structure that capture parity odd term. But we don't, so for us it was good to check it, and that was the priority. So let me summarize, and then with some observation of future thing to say. So I've described to you a set of results which are termed under replacement rule, which is the high-dimensional version of the chiral half of the Cauchy formula. That anytime you have anomalies, you give me the anomaly polynomial, I can tell you the leading parity odd contribution. We constructed, as we know, the first anomalous fluid gravity solutions in general are a leading order for the general Einstein-Maxwell Chern-Simons theory. It would be nice to generalize this to add order states. I'm going to talk about that later. And we found power replacement rule in the calculation of currents and stress tensor response, which after a few steps implied the replacement rule in the boundary. Both the bulk derivation and the boundary derivation are still very tedious and obscure. It'd be nice to think about this carefully physically and maybe more geometrically. And as I alluded before, it'd be nice to think about time dependence, non-stationary black holes, or I guess in this case, non-stationary fluid gravity. Because in the boundary you can think about hydro states, they are non-stationary. And they would have some particular contribution in the field theory that people understood. And you might want to go to higher order in the parity odd contribution. And as I say, if you add matter, etc., could be that what we are doing is sufficient because this is captured essentially the gravity sector of things, and if you add matter, it shouldn't. We expect it shouldn't alter the conclusion because of we believe it's a gravity sector issue. So maybe I should put quotation mark in here. So we also talk about, if you think about hydro thermodynamic properties, there are some that are controlled by anomalies. Are there such things in entanglement entropy that are also controlled by anomalies? Because if you work with entanglement entropy, you think about Renyi entropy, and that's in a sense some sort of a finite temperature type of computation. Temperature is proportional to Renyi index, and you're thinking about it in terms of finite temperature computation. We sort of wrote a paper about thinking of how to think about it, and other people have thought about it. There's some issue because whether you cannot put chiral fermions on the lattice, whether you can really define entanglement entropy. Because usually you define entanglement entropy, the most rigorous way to put it on the lattice and really trace out things outside and inside. So we have some words to say about it, but I'm not going to say too much. Then you can also ask what's the bulk structure that captured. So that's other people in industry know.